Welcome back to Honors Calculus. In this video, we're going to conclude our discussion on extrema with the idea of higher order derivatives. And I'll be perfectly honest, higher order derivatives don't really fit into what we've done in the last three videos for this lesson. Instead, think of this as a preview of things to come. In the next lesson, we're going to take the idea of extrema and try to expand it out and use it to form some tools that will allow us to graph functions fairly nicely without needing to resort to computer graphing tools. And one of the things that we're going to need in order to look at that is to look at how our rate of change of a function changes over time. We call that the second derivative. So let me get my head out of the way, and I'm going to relate this to the idea of kinematics, the physics of motion. Not necessarily because we need kinematics, but to be perfectly honest, the ideas of the derivative first came into existence as a way of studying kinematics. And in kinematics, the question of note is if we have some sort of particle, and what we mean by particle can vary from an electron to a cannonball to the planet Earth. If we have some sort of object, what is its position at any given time? And in order to help calculate that, we also look at things like how does the position change? Right. Now, let's go with t's. Right, I'm going to name my position x of t. So the notation here can get a little bit messy, but I think it helps make sense of what's going on. X is a function of t, not f as a function of x. But if we are analyzing a position, we'll also look at its velocity. And velocity is the rate of change in position over time, which is dx dt, or x prime of t. Then, following that in kinematics, you generally look at acceleration, which is the change in velocity over time. And so we're looking at the derivative of velocity, velocity itself being dx dt. So we can write that as, sometimes you'll see it as d squared x over dt squared. So d squared over dt squared is the second derivative operator. And the function that results of that, we will denote using a second prime, x double prime of t. We can keep going. The names really don't matter at this point. I'm not saying that they never come up, but in the study of kinematics, you very rarely see anyone discussing the jerk of a particle, which is change in acceleration over time. So that will be the third derivative, which we will write as x triple prime of t, and after jerk is snap. which would be the fourth derivative, d to the fourth x over dt to the fourth. And I want to get that far because when you get to fourth derivative, that's where we decide that all these primes are just too messy. And instead, we're going to put a 4 in parentheses like that. Right? It would be 4 primes, but 4 primes is messy. So to shorthand, we put 4 in parentheses. And that way we can naturally expand out to 5 and 6 and 7 and 378, however far you need to go for a particular problem. Like I said, in kinematics, double prime is generally as far as you go. I will be perfectly honest with you. I know of one application in mechanical engineering that uses a fourth derivative, and I know of no other practical applications that use anything above a third derivative. But they exist, we can work with them, and why not? So this being math class, we're not going to worry about things like, oh, there's no application of it in reality. We're going to do it anyway because that's what mathematicians do. So if I have a function like f of x is, say, the tangent of x, well, the derivative of that, we know, is secant squared of x. If I want the second derivative, well, that just means I want to take the derivative of secant squared x. Right? Using the chain rule, that's something to a second power, so that's going to be 2 times that thing times the derivative of secant, and the derivative of secant is secant of x times tangent of x. And just cleaning that up a little bit, we have 2 times secant squared x times tangent of x. If I want to take things a step further, the third derivative means I want to take the derivative of 2 times secant squared x times tangent x. And so I need to use the product rule. I have a 2 in front, which is just going to stay a 2 in front. I'm going to multiply the derivative of secant squared, which is 2 secant squared x tangent x times the second, plus that 2 is still in front, and then we have the first one by itself, secant squared x times the derivative of tangent, which is also secant squared x. Cleaning this up, we end up with 4 secant squared x tangent squared x plus 2 secant to the fourth of x. We could keep going from here. It's perfectly reasonable, but third derivative, like I said, probably good enough. There's no reason to look further than that. Since I'm on the idea of kinematics, I want to mention harmonic motion. We now have the notation necessary to deal with that. Harmonic motion is defined in a couple of different ways. Mathematicians define harmonic motion as any function x of t such that x of t is the negative of the second derivative, x double prime of t. I would like you to take a look at the two canonical examples of harmonic motion, x of t equals sine of t and x of t equals cosine of t, and prove that they satisfy this rule of harmonic motion. Take a few minutes, play around with that, see what you end up with. And I'll see you for the next lesson.